Um, so welcome, I guess, what to be the first installment of kind of a revised, what was the Forge Modeling and Simulation Forum, which was kind of originally intended to be more of a one-way kind of one-way set of communications to give information from the Forge team to the community. What the intent now is to kind of turn this into more of a community-driven event, a much less formal, much more interactive venue to exchange information about a lot of, between challenges people have between modeling, and we'll even, dare I say, go into the part from experimental and measurements as it contributes and supports the modeling programs. So this, once again, it'll be a monthly recurring meeting. I believe today is the third Wednesday of every month, 11 a.m. Mountain Time. And we'll just kind of go through, gently be asking people, some of whom may be funded on the Forge program or the Forge R&D, or else the Forge team itself, to go through and give updates. As a group, we could talk about challenges, about how we conceptualize and how we exchange information. The goal is to make all of us better. We'll just kind of keep moving forward from there. For today, as our initial foray into this revised event, I just wanted to go through. So there are the topic 5 from the Forge external solicitation. Topic 5 is specifically focused on modeling and simulation activities to support the Forge program. So I've asked the 5 PIs, or the 5 teams in topic 5, to give us an overview of their projects, what they intend to do, short, and then we'll go through those. We'll go through all those and we can have a discussion. And I have been fielding some questions, or the Forge modeling team has been fielding some questions about ways to do things, what we're doing. And so we'll use this as a way to just have open back and forth dialogue. We will record all these meetings. This is being recorded. It will be posted on the Utah Forge website, likely under the page for the Modeling and Simulation Forum. We'll keep them all there. And so we'll have these for posterity and future reference. I will say, if you have any further questions, there is a specific email set up for essentially people to write into the Forge team so we can manage and track all those. And I'll ask Gosha or Chris Teese to post that email address into the chat for this. So I would discourage people to email directly to someone on the Forge modeling team, because we want to make sure we capture and track all these conversations. So if you email into the address set up for these, and then we will actually make sure that we post the responses and keep these things so we can kind of keep track of all these conversations and avoid some of that. So one other thing I want to point out here today too is I want to apologize, Ahmad, if you're on, Ahmad Ghassemi. I misspelled your name when I first sent out the agenda. I apologize for that. In the rush of autocorrect and fast typing, I apologize. So
no problem. Yeah, no.
All right, sir. I know it's just a faux pas on my account, and I apologize for that. So, without further ado, I think what I intend to do is just hand these off. And I know the topic 5 awardees did give a short presentation to the STAT a month or so ago, and I expect that many of you will rehash some of those for this larger community. And so, Kayla, are you here? Can I hand it off to you? I expect you to take control of the screen and drive your own presentation. The 10 minutes is kind of a loose guideline. We can be informal here. I will say that Mukul Sharma, who is a topic 4 awardee, he had something come up. He won't be able to be at the meeting, but he sent me a recording, so I will play that in his stead. And Derek Ellsworth, I believe, teaches from 11 to 12 today, so he'll be squeezing in here after the top of the hour to give his overview. So with all that, Kayla, and actually pronounce your name correctly for me. I apologize for not asking you ahead of time.
Hi, Rob. Yeah, sure. I'm ready to go. So I'm just going to take control of the screen.
And pronounce your first name for me. Will you repronounce your first? Is it Kayla or Kyla?
It's Kayla.
Kayla. Okay, thank you.
No problem. So I won't go through. Oops, sorry. Can we see my PowerPoint here? And
it's in presenter. It's not. Yeah, we see it in your. Okay. Yeah. Switch your screens. So we see the.
Oh, perfect. Switch the screens.
Thank you. You're good.
Oh, it was good. Sorry about that. Sorry, this is good.
Switch it back. Okay, now it's good. Perfect.
All right, perfect. So I won't go through the whole thing. I just really wanted to focus on this figure on the right here. Our project is really geared towards developing and testing an end-to-end modeling capability with based on full physics modeling approaches. So what you'll notice up here at the top, we see the traditional THMC modeling, and we will do a fair amount of THMC modeling, but the real innovation here is to couple the results from those types of models, so the stresses and the pressure conditions that exist during circulation, and then extend it to this E component, which is the earthquake component. And that this earthquake component here at least has something to do with computing full ruptures of earthquakes in geothermal systems and in the subsurface. And this is something that really hasn't been done before to high fidelity. And so in order to oh, and then I guess I should also say that traditionally we have done some similar types of workflows, but they are typically using just values of parameters that are from the literature or something, and kind of taken from one side or another. And it's quite difficult and to come by all of the data sets that we do need for a THMC plus E workflow at one site. And so that's where Forge really offers us the opportunity to gather data at a single site and to constrain our models with that data. And further, we intend to take the site characterization data that's already been done by the initial Forge team, and we're going to add some additional experimental work packages on top of that. So we'll do a bit of geomechanical rock strength experiments, and then we will also look at doing some rate and state friction experiments on Forge samples to constrain some of the parameters that are relevant for earthquake sequences. And there's two parameters in this case that actually control whether or not an earthquake will slip seismically or an event will slip seismically or aseismically. And we intend to look at that with our full physics end-to-end workflow. We'll also do further geochemical core flooding experiments to constrain the permeability evolution through time. Each of these types of experiments will provide a data set that we will use in addition to the existing data that's been recorded at the Forge site to develop probability density functions of the parameters that are relevant for the poromechanical modeling, which we'll do in this task, and then the parameters relevant for the earthquake simulations, which will be in the final task. The probability density functions allow us some understanding of how a particular parameter behaves, what its end members are, and we can sample those PDFs randomly and then perform tens of thousands or hundreds of thousands of simulations to constrain the uncertainty in the parameter space and understand how things like aseismic slip and seismic slip behave under a range of parameters. So that's basically what we're working on in a nutshell. I know it didn't take quite the 10 minutes, but we can either, I can answer some questions if anybody's interested, or just move on.
Okay, I have questions, but sure. I will open. I think it's better to do questions as we go, even if we run late on time or back and forth. So I'll open up to the room first, and unless we get a whole bunch of people speaking on top of one another, I'd say just kind of chime in and ask a question. If we get too many people asking at one time, I'll ask you to raise a hand or type a question in the chat. So any questions for the team? And I warn everybody, if it's silence means I get to ask a bunch of questions. So, okay, since it's silence, I have a few questions. So when you say, earthquake and full rupture, will you be actually doing seismic wave propagation in your codes as well?
So these particular codes do not do the wave propagation component. You can take a slip distribution, say this one here, that has a finite amount of slip in space and in time, and then use that to propagate waves through a wave propagation code. So there's some trade-offs with the simulation methods. The full waveform type dynamic rupture type models are highly computationally intensive, and so that reduces the total number of simulations that you can run. Also, those types of models are generally for larger earthquakes, something larger than like a 5. These types of simulations that we run, we're able to simulate earthquakes based on the size of the elements that we use in the model. So we can get magnitude 1s or so, and you get a finite distribution, just like we're showing in this figure here, of slip as a function of space and time. So you get earthquake locations as well. And then slip speeds can be generated too, and to distinguish between whether or not an earthquake is slipping fast or slow. So that's will give us a control on aseismic or seismic slip behavior under certain conditions and the propensity for that.
Okay. So, what I like to be able to do is, as much as we can, use your work and integrate into the site work. And so I kind of see us all becoming one big team.
Yeah.
And so, we actually have put a workflow in, not rigorously, but we actually have done some fault rupture work. And, the reservoir similar code we're using for the Forge team proper, there is a companion code on the same code base that does full seismic wave propagation. But as you said, yeah, these things, we run those on HPC because the meshes have to be so small to get the right frequencies in those waves. So we don't have the luxury of, well, look at your 4 for those distributions of velocities. We just have pretty much slip patches and just looking at roughly pressure changes. I'd like to start talking about when you get to the point where you're getting more mature into there and look at these things, that we can look at ways to help inform some of the site planning models that actually give us full ground acceleration, because that's things we have to look at, with all the other things at the site for the windmills, for the pipelines, things like that we actually have done some screening on. Everything, that's negative, magnitudes that are -2, -1, it's negligible, but it's still something we're trying to look at just for peace of mind. So let's stay in touch with that. And as we go through these meetings, maybe, on our quarterly updates, we'll keep talking about that.
Yeah, that's actually a really good point. And on some other work that we do at Livermore, we do take ruptures that are generated by this same earthquake simulation code and use those to calculate ground motions with an internal wave propagation code that we've developed. But so yeah, that workflow does exist, and I think it's a really useful one. So if you guys already have the capability, I mean, we haven't included that aspect of it in our particular project, but I'm happy to provide output that you can use for the wave propagation.
Awesome, that'd be great, cool.
Yeah, fantastic.
Other thing I have point is, when you start doing your flow through experiments, I will openly admit, I think, I would love to have some site specific reaction rate information. I think that's a big lacking for the chemistry part. We have some equilibrium stuff, and most everything else is from literature. So that's what I'm really looking for to all these projects that are doing chemistry. As soon as as you get experiments done, please start posting any information you have for anything we can get some rate-based information for short time. I mean, and also, we have, for the kind of fluid we're going to be putting through these things, I think we can get you some water sample information for the fluid we're using for the stimulations and for the flow through. So that is, I think, critical and short term. So as soon as we get those things going, please keep the team up to date and the rest of the team as well. So
absolutely, I think that's a really important task, and when we thought so too, so it's why we incorporated it here.
Which is why you got funded, yeah.
And then I guess the other thing about the fluid circulation and fluid samples, or at least chemistry of the fluid that's being injected, I think that would be really useful for our project. So I'm not sure we had intended to disseminate results to the Forge team and through the GDR, but if there's a more direct route to do that, at least for like water chemistry, when we get the project or the experiments up and running, that would be really useful.
Okay, let's put a pin in that one, keep talking about it. I don't have, we have to go through the normal procedure of the GDR and all that, but I think we want to make sure we're just really time sensitive in these things.
Right.
And I will kind of a plug. I'll post a link in the chat here. We have done some equilibrium modeling, looking at different water chemistries for different inject dates and fluid rock in situ chemistry. I could send a link to that where we did some example calculations for us for baselining. So we can start comparing against those and maybe make a more formal way to do it. I'll have to work up with that. I see Kevin England has a question. Kevin, come on in.
Thanks, Rob. Hi, Kayla. I think you guys just I raised my hand and you got onto some of the answers to the question I was going to ask, which is about the geomechanical, geochemical relationship and testing there. I was curious about, if you would do geomechanical determination before and after the geochemistry experiment. And I was curious as to what fluids, yes, you were going to try to flow through the rock samples.
Okay, so that's a really good question. I don't know if my my chemists are on the call right now that could answer that question better than I could, about at least the water chemistry. We said that we would use forage relevant fluids. That's why I asked about if we do have any indication of what the chemistry would be. It would be super useful for us to have that information before we start the experiment. So that is something I'm going to have to get back to you on. And then the question about how the geochemical and the geomechanical experiments will interact. Yeah, we were really excited about trying to do core flooding experiments before and after stresses were applied to the rocks. And even, so there's the group at Lanel, Luke Frosch will be doing the mechanics experiments. And then Chris Marone at Penn State will be doing the rate and state experiments. And you can imagine that some gouge would be developed on the surfaces when two rocks are sliding in the friction experiments. And we thought that core flooding through each of those samples would be extremely useful before and after. The only difficulty there is logistics. It's getting, one, it's transporting samples from each of the labs. So the geochemical experiments would be done at Livermore. So we'd have to get the Lanel experiments in the same shape and size as can be done, are used in the core flooding experiments at Livermore, and then we have to transport them back and forth. So we're still working out the fine details on how to exactly do that. It's looking a little bit less like we'll be able to do experiments on the core flooding experiments on the rocks that Chris uses for the friction experiments, just because the size of those is a bit different than what were our apparatus for the chemistry. But there is hope that we can at least transport some samples back and forth and use the same samples for some of the rock strength experiments and the chemistry.
Okay, perfect. Thank you very much for that.
And we also have written in the proposal that we will do some tomographic imaging of the surfaces before and after the chemical experiments are done, to see the changes in fracture aperture and topography on the surface and things of that nature. That's actually could be useful in upscaling the stress concentrations on like a fracture or a fault for the earthquake simulation, or at least deriving some parameters that we can then use for a statistical distribution of the stresses.
Sure.
I want to move on. We got one more question. I had another comment or thing, but I'll save it for later. Hong Q, did you have a quick question for Caleb?
Yeah, it's a quick question. And I wonder how to represent fracture systems. I mean, in your lab system, relatively simple fracture network probably, but you're showing here is a fracture network as a represent.
Yeah, that's right. So this is one of the largest outstanding questions that we have, and where the true research and the geomechanical modeling and the earthquake modeling will be. We have some ability to incorporate a DFN in or some type of fracture network in our code GEOS X or GEOS at Livermore that we're going to be using for this modeling workflow. There are some pre-existing meshes that exist. I know I talked to Rob about his a bit, and another team as well. I think that perhaps just because of the type of mesh that we have to use for the code, we might have to regenerate it ourselves, but using the properties of the existing models, and then hopefully aligning those with any of the site characterization information that we can get. And then we've not ever incorporated a fracture network in RSQSim, which is the earthquake simulation code we'll be using. In theory, this will work, but I've not tried it yet. So we'll definitely see. I have done randomly seeded faults though, in various orientations. And the only difference between that faults and fractures obviously is the length scale. So we'll be trying to push the limits and the boundaries of the code to see if we can incorporate fracture networks in there.
Yep, thanks.
Sounds good. I'm going to move on for the sake of time. And David Lochner, I saw you earlier, I think, in the list. Are you here, sir?
Yes, I'm here.
Will you take the screen?
Okay, let's see if I can make this work. No.
While you're doing that, I just want to I'll keep chatting while you get your screen up.
Okay,
You have an update coming that we're going to post to GDR and to the Forge website for the Forge team's phase 3 model update. So we revised the mesh, we revised the size, the orientation, as well as a revised parameter set for its native state, pressure, temperature, and stress. We can talk. Let's talk about it at the very end. I'll get into details on that. We don't see your screen yet, though, David.
really? It says that I'm sharing.
At least I don't see it.
Yeah. Well,
If your file's not too big, you could email it to me and I could run it for you, and we could just
Did
move
you
on.
press share? Did you press share in the bottom right corner?
bottom right corner of the Zoom meeting. Start video. Oh, maybe that's what I have to do. How about that?
We got your camera. We can see you now. We still don't see your screen, but we see you. So you have a nice sunny day wherever you are.
Yeah, right. Well,
Maybe it's snowing in Idaho. Typical spring
share
day.
screen. How about that? Did that do anything?
Not yet. Yeah.
It's a 3-step process. You have to select the screen you want to share.
Yeah.
And then at the bottom right, there is a small blue button you need to actually initiate to
Yeah,
throw it
well,
to share.
there's no small blue button.
Yeah. Email me your slides if you would, and I'll share them for you.
All right.
And while hopefully it's not a 40 megabyte file, but I could take up to 25 megabytes, I think. Via email.
Okay. I'll send it in here in a second.
And what I'll do, actually, Ahmad, can you kind of come in and we'll just switch places? You're muted, sir. If you're
Yes, I can. My PowerPoint just froze. Just give me 1 second. to
It
open
figures.
it up.
That's the thing. This isn't more to be an informal meeting, so let's not. We won't worry about too much of these things. They'll iron out as we go.
Okay, I think I can do it just now. Let's see. Download.
And I'll watch my email for.
Okay, so let's see. Share here. Okay. Share screen. Okay. Jeez. Now he's trying to do all kinds
Looks like
of
it's trying to do something. We don't see it yet, though.
Okay, let's see. So can you see my screen now?
We see a Windows blue screen, a window with a window on it.
Okay, that's odd. Let's do another. How about this one?
Now we're cooking.
Okay.
If you want to hit it in the presentation mode, we still see your.
How's that?
No, it's actually, it thinks it's your second screen. Go back to the way it was and just go from
Yeah,
there.
I'll just
Yeah, perfect.
do
That's fine.
this. There
Good.
we go.
Okay.
Okay, so our project is mostly an experimental one, but there is a modeling component attached to it as well. So the main focus is determination of thermal mechanical properties of the Utah Forge reservoir rocks, or rocks in the vicinity of the reservoir, depending on what kind of core we get. Okay, now it's trying to. Okay, well. I don't know why it's doing this now. Okay, save, browse, download, save. Okay, now I can get out of that save one. So, and the objective, of course, is to be able to predict, forecast the response of the reservoir to stimulation, both in terms of permeability creation as well as microseismicity, and to, in general, get a better appreciation of the role of coupled processes during reservoir development. And so, one aspect of it that I think that I forgot to mention is the fracture closure process. So that pertains to the issue of what technique provides a better result in terms of determining the closure pressure. So we would like to explore that experimentally. But before that, we'll conduct standard poroelastic tests on intact rock. That was the idea. And then we would also do these measurements at higher temperature, depending on the stability of the system. We'll, go to 150 probably. I'm not sure if we can go higher. We'll see. And then we will also design new experiments to determine poroelastic properties of fractured rock. So that is something that has not been done, and that will, once we're successful to do that and obtain the data, we can use that in dual porosity, dual permeability numerical models for reservoir simulation. And the hydraulic fracture experiments, they'll be done in a polyaxial frame on blocks of rock that are up to, say, 13 inches on the side. And again, we will have a series of experiments at room temperature and then some at higher temperatures. At the same time, we'll do some numerical modeling to not only help design of the experiments, but also to see which parameters are actually more important to measure. So obviously, we know that Beal's effective stress coefficient and Skempton's pore pressure coefficient are important. So we'll try to see if there are others that we need to focus on or not. Or can we come up with a more efficient way of determining these properties, say, indirectly? So come up with some kind of a relationship or correlation between different approaches to determining these properties. So as you know, we need, what, 4 plus permeability to characterize the rock. So 2 are just the elastic properties, Young's modulus and Poisson's ratio. The other 2 are different people use different groups of parameters. We usually try to use alpha and B.
Mm-hmm.
And then we have some results actually. So I want to show you these. We had some plugs from well 5832, and we measured the intact rock permeability first. And so you can see on the lower right that the intact rock perm is very low, obviously, and it's stress dependent, as you would expect. And as you increase the effective stress on the rock, the permeability declines. So the mean effective stress that you would expect, I guess, based on our current understanding at during the near the stimulation zone, is probably 27, 30 MPa. So you can see, that matrix permeability is very low, order of maybe 50 microdarcies or so. And different rocks obviously have different matrix permeabilities. It seems sample B, for whatever reason, is very tight, and it just could be that we just got a very kind of a uniformly a uniform composition, very little porosity or fractures in that particular zone. It's possible. And obviously, the larger strip permeability is much larger than that. Now, so that's just permeability on the side. But more importantly, we have some data on the values of alpha, and so if you guys want to see the details, we have an upcoming paper the ARMA conference where we present this. So what you see here is again at about 35 or so, or around 30 MPa, which should be the mean effective stress near the reservoir, you get Beal's effective stress coefficient of about 0.6, 0.65 or so, which is kind of higher than expected. So, some of the modeling we had done in the past, we used the data for westerly granite, and that's about 0.4, 0.45. And what is also interesting that, we have other techniques that we have utilized to determine this coefficient indirectly by measuring, say, K and KS, that is the bulk modulus and the grain modulus of the rock. And there are some differences, but not major. So there's a nice, kind of consistency in the obtained results. And so that's encouraging. And this is again for just intact rock.
So can I interrupt?
Yeah.
So this is interesting. I haven't seen these because we originally did some of these. We started out with just a literature value of around 0.6. I think we first started doing some of these simulations, and then we did some internal analysis. And I'm going from memory here, so don't hold me to this, but I think we were looking at a value of like 0.5, 0.47. Looking at, but and so now you're skipping. Looking at that's at reservoir stress.
Yeah.
So at 30 MPa. So, depending on what your sample is, okay, so we're in the range, but maybe you're coming up a little bit higher with all your samples.
Yeah, a little higher. I think
Yeah.
a little higher. And so again, these are, smaller samples. And so whatever cracks that are present are micro cracks, so, what will happen if there are more cracks around, we'll see. And then theoretically, you need to consider the response of the fracture independently. At the same time, you would need different coefficients for that. So, that's probably future work. So we'll discuss that then. But yeah, so if you're in the range of say 0.45 to 0.65, 0.7, that's good. But then keep in mind that during stimulation, you will increase the pore pressure more so that, you go to the left side of this curve.
Mhm.
So, it can get to, to even 0.8, depending on, how much pore pressure increases in the rock. So.
Ahmad, this is Dave Lochner. Since we're interrupting here, I just was wondering, what was the in situ temperature that these?
Oh, these are room temperature. These are all room temperature.
But where did they come from? The depth?
Oh, these rocks. I had it in the previous slide. Let me see here. About 6,000 to 7,000 feet.
That would be in the order of like 170 C, give or take.
Yeah.
They're about in situ.
Yeah, 177. Yeah, that's right. Yeah.
So when we would measure cores from deeper drill holes, especially granites with quartz in them, just cooling them down because of the the properties, thermal cracking would happen in them, so that what you have at room temperature may be a very much higher permeability and coefficients like this than you would get in the natural state. So
yeah, so
recover that
right
from a surface sample.
Yeah, so the thing is, we apply. Obviously, we try to replicate the in situ stress conditions to see what the stress sensitivity is, and some of those cracks tend to close. The ones that were introduced, hopefully, so that some of them will not close, and obviously will be reflected into this. But there's not a whole lot one can do. I mean, even if we increase the temperature, there's no guarantee that we can replicate the subsurface conditions that existed before taking the core out, because you will still have differential thermal expansion coefficient, which may create additional fracturing. So it's kind of it's hard. But again, keep in mind that on a larger scale, the rock has probably more fractures than the intact rock. So, if we introduce a little bit in the intact rock, it's not so bad after all. So, it's one of those things that we can always kind of wonder, how well do we replicate the actual reservoir conditions? But yeah, well, that's a good point.
Hey, Dave, this is Steve Hickman. Can you hear me?
Yes.
And Ahmad?
Yes.
Yeah, nice stuff, Ahmad. So one question I have related to Dave's question is, could you measure velocities, like P-wave velocities on these samples, and compare them to geophysical well logs?
Yes.
to see if you can, because we know that, you know, P wave and shear wave are very sensitive to crack density, and maybe you can address this issue of residual thermal crack damage by comparing logs to P wave measurements made at these effective stresses.
Yes, we have those values. I believe we do. I'll have to double check and see what stress level they were conducted at, the experiments for the dynamic values. And we haven't really broken the samples yet. That is, we have not failed them. So even if we have not done those at those higher stresses, we may go back and repeat those. But yeah, we can do that.
Okay.
Yeah, so for sure. So I think when we, I'm trying to look at the report here while I'm talking about this. You know, I think there was a small stress applied, maybe a couple thousand PSI or something to the sample when we did the dynamic measurements. So we'll have to go and repeat those probably. But yeah, so that's a very good point to get an idea of the extent of secondary cracking by comparing the sonic data.
Yeah, we did some measurements like that on the Kohler core, Lev Vernick, in a paper, and I'm looking at it now in 1994.
Okay.
And if you haven't seen it, I can send that along. And that was,
Yeah, sure.
that was a classic case where we had residual damage, and Dave's referring to other papers. We can pass those along too.
Yeah, that would be nice because it will save time too.
Yeah.
Yeah, and Steve, if you'd send those to me or send me that address that was in the chat, I'll start a little somehow a little shared area for this meeting that way everybody can get to and just grab, you know, depending on how the copyrights or whatever we can do. So, Brian, I see your hand up. I'm going to let Ahmad go to his next slide if you're okay.
Yeah, I got two more. Then, okay. Yeah, maybe if you know, I don't want to take other people's time, but and this is the some results for the Skempton pore pressure coefficient. This is tough to measure, so the results seem reasonable though. I mean, we can still see the stress dependency that we saw in the value of alpha, so that's fine. But again, at lower effective stresses, you get much higher values as you would expect. But reservoir conditions, probably around 0.5 or so, roughly, depending on the rock type. And you will see that the rock type has a significant influence here. So the diorite, I think that's the darker colored rock right here, sample C. Yeah, so that has a lowest value here and highly nonlinear the way it changes with effective stress. So we used water in these experiments, and so it's very challenging to get full saturation. Then you have to wait around for a bit once you change the confining pressure to let the pore pressure to reach equilibrium. So it's kind of hard to do these tests, but again, it provides a more kind of a educated guess or estimate for the B value that you would expect to get. And so with these values, then it would seem to me that at least, you know, if you consider the intact rock in your analysis, that, you know, the pore elastic effects can actually have some significant impact. And so,
Ahmad, let me interrupt. I see you're about finished.
Yeah.
I'm watching the clock, and I don't want to. I want to judge, actually get a feel, you know, from the other speakers, whether you prefer that maybe some of you would speak and talk about your stuff next time in favor of a longer, more in-depth discussion here.
Yeah, I'm done actually. So that was the last slide.
Oh,
so,
I wasn't trying to stifle, but I see Steve has a question, Brian, and I think, somebody dropped their hand, but Rick, I think it was. So HonQ, Derek Ellsworth isn't here. I think when we get to David, we get to you for sure. What do we prefer to do as a group? This is meant to be Pagorni telling just, you know, saying how it's going to go. This is a community engagement. So I guess if you want to just keep having conversations, you could probably, I think, there's like a reaction button in the bottom of your screen. If you click reaction, like a thumbs up or a clap your hands, we'll just keep the discussion going as we go, or I'll just kind of stop questions and move on. So it'll just be totally driven by the room. Do that right now if you can figure out how to do it. Otherwise, Brian, ask your question while I'm waiting for that, since you had your hand up the longest.
Oh, thanks. Hey, Ahmed, great presentation. I just had a quick question. In your your microfrag test, and maybe your last slide answered this question. Are you able to add some shear component in those micro fracking, or are you just getting tensile opening?
It is possible. I think we're just going to go with tensile initially. It is possible to do shear, but it would have to change the complexity of the experiments. It's doable. In principle, it's doable. It wasn't part of the scope of work, but you know.
Right. I'm wondering if at the Forge site, if maybe Rod knows this, if tensile fracturing is more common, or if you should expect some shear component. Anyways, that's just kind of an
both. You know,
you.
so I mean, they're planning to do different kinds of stimulation. So I suspect for the ones that are more likely to be tensile, you know, that would have some relevance. But
You know, from our planning models for the stimulations, depending on where we try to initiate, where we do the perforations, whether it's open hole, we are targeting areas where we see a high propensity or high density of, I would say, I'm going to air quote, critically stressed pre-existing fractures. I'm not saying those fractures are open or have permeability, but they are detected in the FMI logs and at the right orientation where they should be most amenable to be stimulated. Whether that's, and most of that would be either, it would just be reopening or some shear on those things. We did see some tensile failure, but usually those get fairly short and get arrested into the natural fractures if that natural fracture domain exists, if it's going to behave the way we expect. So,
but you know, like for DFIT, but
Yeah.
for the microfrac, then you gotta do
So,
tensile.
Steve, I'm going to skip over you in favor of Rick. You want to ask your question, Rick? Then I think I am going to move on, Steve, but I'll let you can opine as much as you want. We get back to a more open discussion, if that's okay with you, sir.
Okay, well, thanks, Rob. I'll keep it pretty short. I mean, I appreciate the invite to participate. So this comes more from your experimental work, and was, what did you do to confirm saturation? And the reason I ask that is a bit of a selfish thing, is that we're doing a bunch of petrophysical work for granites for site assessment, site characterization in Canada, for siting for nuclear waste. And one of the challenges with this class of materials was, you try and saturate them, but any thoughts about how you confirm the degree of saturation?
Wait for a long time and then, you know,
Okay.
and then check the response of the pore pressure. See, you know, how quickly you can see the change.
Yeah,
You know,
but that becomes for us, it becomes a bit of a challenge because you never know what's happening on the inside of the sample.
Yeah, I mean, there's, you
Yeah,
know, and it's
right?
likely that there are, again, heterogeneous pore pressure fields within the sample. It's you know, very likely. Yeah.
Okay, good. Yeah, no, okay, appreciate it. Thanks.
But you know, but for the for the values of alpha, we use argon gas, so that you know reduces the problem somewhat. But for B, you know, we just use water. So
Yeah. Okay, good. No, appreciate it. Thank you.
Okay.
Thanks, Rob.
Thanks, everyone. I'm going to move on. David, I have your, hopefully everyone can see your slides on my screen.
That looks good.
I'll drive for you. You just tell me when you want me to advance.
All right. So this is our contribution to the research here. We're doing measurements of permeability and strength recovery in fractures, either natural or simulated at this point, mainly simulated fractures. And you can see the team here. It turns out it's all USGS at this point. I'm not sure. We tried to expand that, but in the end, we ended up being all USGS personnel here. So if you go to the next slide, thank you. Our objectives are to look at, as I say, fractures and faults that respond to THMC interactions at different scales, length and time, and we want to identify and measure the rates of change of fracture properties under hydrothermal conditions, parameterize the modes of reaction, develop the micromechanical and empirical fracture models that could use these parameters in the modeling and extend that to first laboratory scale and then reservoir scale modeling applications. So next slide. If you would, we have 4 elements, major elements to the program that we're being funded for. The 2 of them are experimental. The first one is a standard triaxial geometry shown here, with a 1-inch diameter cylindrical sample with an inclined saw cut in it, and boreholes drilled into the saw cut so that we can flow water along the fracture and measure permeability. At the same time, it's heated and in a pressure vessel so we can control confining pressure, normal stress, and by advancing the piston, we can shear the sample as well and measure frictional strength and permeability evolution. So we go up to 250 degrees centigrade, and a typical experiment like this is a slide hold slide test, generally just by what is reasonable up to a little over a day for the longest hold periods. And as you can see on the upper right, we do some experiments up to 5 days. We've gone out to about, I think, 20 days in one over the Christmas break where we weren't interrupting the system for a while. So what we measure, as I say, are time-dependent fault healing, re-strengthening, and permeability evolution. So the top right panel shows results from a bare surface granite on granite saw cut. The two blue data sets dots in there are room temperature. The upper figure, if you, yeah, there. Those are room temperature healing rates. What you find in these experiments is that essentially log linear behavior for re-strengthening versus log hold time. This is in coefficient of friction. The gray and black symbols are at 200 degrees, and we see the typical re-strengthening up to roughly 10 to the 4 seconds. And then we see what appears to be a new deformation mechanism kicking in that actually starts weakening these samples with time at longer hold times than 10 to the 4 seconds. So this is something that is a little unexpected for us, and we're investigating currently. This is all only happening at the 200 degree tests, and the room temperature tests all just show log linear strength increase. At the same time, the lower panel on the right shows 3 experiments. Actually, these are 3 runs out to about 5 days each. The upper blue is a room temperature run showing a drop of maybe 20% in we'll call it transmissivity, essentially permeability after 5 days. The 2 heated experiments, the black and red, are showing about 80 to 75 to 80% loss after very rapid loss in the first day or 2 in terms of permeability, and then a longer decay. So these are the kinds of measurements that we're providing.
So this is fascinating work. I'll just interrupt, hope you don't mind. So it's when you pull those apart and look, is it like pressure solution on the asperities or just kind of melting together, or what's driving that reduction?
This is work in progress. This is we're doing SEM work on these samples, and as I'll show in the next couple slides, we're going to do surface profiling characterization, but at this point, this is observational. And we do have results. Let me just mention just briefly in some pure quartzite samples that indicate that there is no increase in cohesion in tests like this in the pure quartz system. So it is all either compaction or some kind of frictional process, not a cohesive re-strengthening of the contacts. So that's work in progress, though.
Okay.
So here's the other experimental setup. It's a hydrostatic system, and this is a single contact type measurement that is done. You show a pressure vessel on the left here with 2 quartz crystals contacting at a polished surface or roughened to some preset condition. And then that sample assembly is blown up. And the right, there are two geometries. The blind geometry is what we're looking at is the aperture change of the interface between the two quartz crystals with time. Essentially normal loading at temperature and normal stress on the surface and controlled pore pressure. We have experiments running like this right now. Steve has been involved in this. Mostly Nick Beeler has been running these experiments, and on the right we will set up to actually use electrical resistivity of the fracture interface as a proxy for aperture changes. So look at the evolution of electrical resistivity during these long-term bake tests that we're going to do. Okay, the next slide. What we'll also do is look at surface profiles, either on very different scales, from electron microscopy to optical microscopy, and then scanning high precision 3D surface profilometer measurements. This is an end member case. This is not from this study. This is a 3-inch diameter core that I broke in the lab, just showing that this is a very rough surface, sort of a natural fracture surface that you get in the laboratory test. On the right is a 3D image of this that could be used to look at aperture and do numerical modeling of offsetting the two surfaces and looking at aperture change over something as rough as it. The roughness here is on the order of centimeter. Most of the experiments we do are on 1-inch samples or smaller and with saw cut surfaces. So the roughness will be on a quite a bit smaller scale than this. Okay, and the final slide here, we take all of this. Josh Tyrone is our modeler in this. He will be using the rate constants that we measure in the physical experiments and putting them into THMC type reaction models like Tough React. And first looking at the laboratory scale samples to work out a direct comparison between lab tests and the modeling. And then when that is, we have a handle on that, then going upscale with that to the reservoir scale. There was some talk about fluid chemistry. We have some capability of controlling fluid chemistry during these tests, probably more salinity than anything else. And we have plans to possibly look at that as well. So I'll leave it there.
Thanks. Any questions for David?
I have another question, but maybe a suggestion on
Sure.
on the roughness. I mean, if it is possible to calculate the roughness coefficient, that would be very nice. Then we can all kind of compare values. That is, if you take a profile of the surface, then there's some analysis that can be done with that with some equations.
Yeah. So
then
that,
you can get a roughness coefficient. Yeah, Jones roughness coefficient, which is I mean they use that in geomechanical analysis. Blah blah. So
certainly that you can do that kind of testing, but also with the precision profilometer measurements, we can compare two surfaces in contact and then shift them and look at how the contacts are changing with shearing and what that implies for, for aperture, that sort of thing.
That scan, or the 3D scan you showed of the core, is that something you could share?
Well, that one is just a preliminary. It isn't even part of this study. Soon, Brian Kilgore is on. is here at the meeting, and he's been looking at the profiling. We've been looking at different ways of doing this because we are in sort of a funny range between the precision we want and the surface roughness that various instruments can provide for us. And so we're exploring that right now. And I think very soon we'll have profiles that could be shared.
Okay. Yeah, the reason I was asking is I have some interns who come for the summer, having them mesh and just do some flow through that crack and have both sides and move it around. It'd be something interesting for them, a project for them to try to mesh it. So that's the only reason I was asking is high resolution. Is Josh on? Or Josh, are you here? So I'll relate some questions. I have some questions about, your second point here for incorporating these aperture models into reservoir scale simulations. That's a non-trivial process because you're talking something that's on the micron level into something that has grid cells in the 50 to 100 meter cubes. Really get some details how he's going to plan on upscaling that and something, into something like Tough React. You can look at some embedded subscale models or just in general, what the overall plan is for that. Don't need an answer right now. And, especially getting those really aperture scale models, you see thermal versus chemical versus mechanical. Is any one of these teams going to be doing some detailed thermal expansion measurements? I'm just curious. And that's not to you, that's just to the room. I don't need an answer, but I think that could be very critical. I think in some of these things, especially and how that relate to different bulk chemistry and bulk mineralogy of some of these rocks. How quartz rich different zones are, they may react quite differently thermally for expansion or contraction.
Yeah, we might be measuring some. I think we'll measure some. Yeah.
If you could, that'd be great. I see something popped in the chat. I'm in presenter mode, so I don't see things as easily.
Yeah, I don't have any right now, but
Okay.
I think once we start doing the higher temperature tests as part of the data output, we can calculate the expansion coefficient. Yeah.
We did commission some thermal expansion laboratory experiments for the Forge program. I will find that report and share it. I'm sure it's on the GDR, but I still find it out and share it with everyone just so we all have it. Steve Hickman, you want to ask a question? And then from there, I'm going to move on to Hong Q.
Yeah, sure. I just wanted to elaborate a little bit on the single crystal work because you asked a question, Rob, about intergranular pressure solution. And one of the things we're doing is pulling that. We have the first sample out now. We'll be pulling it apart and doing some very high resolution down to the nanometer scale profilometry. Looking at that, looking for overgrowths, indentation, fracturing, perhaps things that might be happening at the asperity scale. So address the relative importance of cementation processes, crack healing, and intergranular pressure solution by doing some after annealing examination with profilometry, optical microscopy, and SEM. And we'll also be doing, Nick and I are starting another experiment right now where we'll be doing some similar measurements at different fluid pressures. So we're looking at the effective normal changes in effective normal stress on these processes. Obviously, it's very important to know what the true effective normal stress is on these fractures, to look at the closure process as well as the mechanisms and kinetics of closure in this chemically reactive environment. So just wanted to throw that out there.
Thanks, Steve. Derek, I see you're on now. I see you're here. We're running about 10 minutes late. Actually, we're running 20 minutes late. I'm going to actually go to Hong Q right now to give an overview of his project. I mentioned before you came on, but McCool he couldn't make it today. He sent me a video I could play of him, but since he's not here, once Hong Q is done, we'll just go straight to you if you have time to wait.
Okay.
Thank you. Okay, great. It's all you, Hong Q.
Great, thanks, Rob. And yeah, our title is Role of Fluid and Temperature in Fracture Mechanics and Coupled THMC Processes for Enhanced Geothermal Systems. And I mean, probably share many commons with other projects in terms of THMC effect as well as fracture mechanics. And so our project include both experimental and numerical components, pretty equally distributed. And here I just listed our modeling team members. And also we include some John Rudnicki to develop some theoretical modeling. So probably upscaling part, some John's work may really help out some other project as well. Also, we probably, when I look at some other project descriptions, yeah, some of experimental data will be really useful for our project as well. So in terms of experimental work, we are going to use two different setups. The first one is mostly kind of shear shear slip testing at Purdue, and then we're gonna actually, mostly kind of biaxial testing setup for SND. We're gonna do some fracture propagation testing using wellbore systems. So we're gonna actually make some synthetic single or dual wellbore systems, and then track some fracture propagation using probably acoustic sensors as well. And those testing data will be used to some validate experimental numerical components developed by Ahmed Albana from UIUC, and mostly kind of multi-scale process, continuous discontinuous skeleton method with some spectral boundary method, so that actually we can simulate a dynamic fracturing process as well as wave propagation. And let me see, I think we can probably move on here. So here, and then after validation of those numerical modeling, so we're gonna actually implement this update version of numerical method into Falcon. So we're gonna actually rely on also a current model as well. And then we're gonna use those updated model for field scale data set, mostly kind of data assimilation as well as some parameter estimation using inversion method. We're gonna employ some machine learning aspect as well. So traditional kind of hierarchical Bayesian framework as well as some machine learning component to perform some advanced data assimilation aspect. And then hopefully we're gonna apply those concepts for more kind of large scale parameter optimization, some other monitoring optimization aspect as well. So here, our team include actually 5 different institutions, and so contracting actually has been quite delayed. Still actually Sandia in process to finish up contracting with Purdue, but almost actually finish up. So we had some kickoff meeting last month, so we're gonna get started actually this month to work on both. So we don't have any result yet. However, as I said, we're gonna actually perform laboratory experimental work, which will provide some data set for developing theoretical analysis. In particular, we really wanna do some upscaling using some latent state model, as well as we're gonna actually using some THMC aspect on those parameters. So I think probably some USGS work and some other projects may help us actually get those data really that'll be really useful. And then, as I said, we're going to implement those theoretical and numerical development into Falcon model, and then validate against the experimental data. And we're going to update those model for field scale. So that's kind of overview of our work. That's it.
All right, thank you. Questions for Hongyu? As always, if it's silence means I get to take first shot at speaking. So, and of course, you probably imagine I would key in on your third bullet there. So you mentioned, some time adaptive discontinuous Galerkin scheme. Can you elaborate on that a little bit? And I actually want to connect you with some people here. We are actually doing a different program, a different project is doing some discontinuous Galerkin formulations for mechanical, for, it's almost, and I think Jerry Liu, I think he might even be on, but I'd like to connect you with that team to make sure that, if there's something that can be leveraged upon one another, we should try to make those connections. Can you comment a little bit more about that, how the space-time adaptive you're doing for the discontinuous Galerkin?
And I'm probably not providing really deep technical details. However, it'll be really nice to make a connection. You know, when you look at some Falcon or Moose kind of literatures, yeah, we see some functionality implemented in those Moose and Falcon framework. So we really want to use it. So here, as long as I know, this space-time adaptive discontinuous Galerkin method has been developed independently at UIUC, but actually Ahmed, I mean, I want to ask him to make a presentation probably in coming months. And he used to test some Moose capability a little bit, probably 3 or 4 years ago. So our intention is to utilize whatever current functionality available in Moose and Falcon framework.
Okay.
And then we're gonna, if we need to update, we're gonna update the Falcon module.
Okay.
But independently, we're gonna develop still kind of some other kind of separate code, but eventually our outcome will be implemented in Falcon framework. That's
okay. Thank you. Other questions from anyone? You get off the hook easy. I'll let you go with that one, but we will follow up upon an independent conversation to dive in a little bit deeper.
Yep. Thanks. Yep.
Derek, I know you're having audio or some connectivity problems. If you want to take over the screen, and we'll hope against hope that you won't drop.
See my screen?
Yeah, did you have slides you want to share, or you just want to chat?
Can you not see my screen?
I did not see your screen.
Yeah, we can see it now.
Oh, you can see it. Okay, I can't see it. Well, go ahead without me. I may.
I can just go ahead for you, Rob, if you want. Can people see?
Yes, I see the screen.
Go ahead, Derek. I'll go without it. I don't want to touch anything because I'm the co-host. I don't want to mess up the broadcast, but we're fine.
Is anyone there? Can everyone hear me? Okay.
I can hear you.
Yes.
All right.
Yes,
All right.
yes.
So I don't want to be talking into the ether. So this is our project. So seismicity permeability relationships probed by nonlinear acoustic imaging. It's partly the same proposal or review that was given to the stat. The project is really attempting to do three things. We're trying to probe the relationship between permeability and acoustics in terms of specific stiffness, both in normal mode behavior and shear mode behavior, to try and see if we can use acoustics to be able to image for permeability in some way, specifically for hydro shearing, and to look at the impact of shear stresses and normal stresses on that, which control that stiffness, contact stiffness in a big way, and therefore control acoustic velocities and changes in them. We're trying to understand the relationship between injected volumes and rates and the magnitudes of the MEQs that come out of that. Certainly MEQs are something that generate permeability, but you want little MEQs, not project terminating MEQs, and trying to understand exactly involved by shear stresses, critically stressing shear stresses. And the third one, to link those together in some way, is to look at seismicity permeability relationships. In other words, being able to take MEQs, their magnitudes and locations, and being able to somehow transfer that passive seismic information into permeability evolution in these reservoirs. So largely the project is in 3 tasks. 2/3 of the tasks are in the lab. I guess maybe, yeah. So the 2/3 are in the lab using the specimens within a core holder to be able to measure end-to-end acoustic response for stressed single inclined fractures, both for the permeability experiments and for the moment magnitude volume relation experiments. And so the goals for these are to do them at temperature and at high stress, be able to do both passive and active monitoring of the acoustics at temperature and stress, and be able to take that to be able to say something about those two problems that we just talked about. Injection volume. And the third task is to use modeling to tie those together. Both modeling at the micro scale using granular mechanics models, PFC, and also modeling at the continuum scale using Tough React FLAC, which is actually a derivative of a program that Josh Tarrant developed when he was here at Penn State. The Gantt chart, which we used before, is there. Task 4 is the modeling one. I'm just concentrating on the modeling really in the few remaining slides, just to give you a sense of what we're planning. So we're doing two things. We'd like to be able to use granular mechanics models to look at rough fractures. So we've done a bit already in terms of having those models relate to rate state friction and the contacts in terms of an evolution function and A and B values for each of them, and also a characteristic dimension. The kind of architecture that represents fractures of different roughnesses, and be able to hydroshear those fractures to be able to see what happens as a result of the strain weakening or strengthening that occurs within these systems. And to use that in different geometries to look at the evolution of friction with different roughnesses potentially, to look at the evolution of permeability, again with different roughnesses, and to also look at the stability characteristics of those in different modes. So these are clearly not from this project, but are just illustrating our interest. And ultimately, what we'd like to use is I guess, the update for project to be able to incorporate acoustics across these surfaces. So be able to look at full waveform behavior in the end-to-end pulsing of the nonlinear acoustic imaging. So nonlinear acoustic imaging means having a low frequency stress or pore pressure pulse that changes the ambient stress and therefore exercises the nonlinear stiffness, with the probing pulse at much higher frequency being able to pick up the change in that behavior. So again, not from this project, but to give an idea of, again, the PFC information that we'd like to pull out of this is experiments that probe by looking at changes in the acoustic velocity, lowercase c in these cases, relative to the pre-existing, the normalizing acoustic velocity, and seeing if there are any linkages between changes in permeability that occur relative to the original permeability, and how those might be linked in terms of the acoustic properties. So that's one goal that ultimately would come out of the PFC work. The second activity would be to look at the two other components. One would be the magnitude of events versus volume injected, and also seismicity permeability connections between the size of the MEQs and relating that to potential changes in permeability. And so we'd use the evolution. This is actually a Josh Tarrant figure from one of his earlier papers. The evolution of this model to look at fractures in porous media and shearing those, again, rate state behavior in this particular model, and to look at, in this particular case, micro earthquakes at Newbury, and use the moment tensor solutions to be able to go through this basic workflow of using the moment tensor solutions to give you both orientation and mode of fracture displacement, to take the magnitude of the events and assume a stress drop and get some evaluation of fracture size. From the fracture size and the knowledge that the roughnesses of faults and fractures have some kind of universal scaling relationship, self-defined fractal scaling relationship, to be able to define dilation, and dilation then is a proxy for permeability changes. And so that's one of the goals for using the continuum model to do that. And these are some prior results, again, from a few years ago that are not this project. So that's it in a nutshell. Hopefully you could hear me throughout that.
I could, although I still never saw your screen, Derek, but
they're beautiful slides.
It is getting recorded, so I'll be able to play it back later and see it as we speak. But questions for Derek? I guess it's Pagorni's pontification time then today. So Derek,
Yeah.
I would say it might be useful to you. I'm not sure. We've been using, at least for our stimulation modeling, Branko and team at Itasca have been leading that work, and they've been using Excite. And so and I'm not sure that how closely related these are to some of the codes you plan to use, but we have come up with a workflow where we can export essentially, the stimulated fracture apertures, throughout the space of the domain. So if some of that kind of information could be useful to you, we can get to that kind of things, at least be helpful for just for the planning models that we've been doing.
Sounds good. So noted. Sounds great. Some inkling of that maybe in the STAT presentation meetings.
Yeah, unfortunately, that day that happened at that STAT meeting, I was out of town and unavailable, and so unfortunately, I wasn't able to opine there. But so I guess if there's no other questions for Derek, and I may have more with you, but I'll follow up via email if I do, Derek.
Hey, Rob, I had a question, Steve.
Yeah, go ahead. Steve,
So Derek,
okay, go ahead, Steve.
Yeah, Derek, that's really nice stuff. And so I'm curious, in this last slide, the dilatation mode permeability evolution, and you're showing work from prior work here. Are you characterizing non-double couple components of these micro earthquakes from field data to compare against the lab? Of how are you determining the amount of dilatation in the field, or is that primarily a modeling extrapolation?
It follows the workflow. So if you assume a stress drop, you can get a deformation magnitude for a given magnitude event, and from that deformation, if you know what the roughness is and you assume that everything rides up over everything else where that's made, then you get a dilation that comes out of that. And
Okay, that's how it's determined.
Dilation in the aperture, and these are relatively low permeability rocks, presumably, and so we would get a change in permeability as a result of that.
Okay, and that's not, is that using shear dilation angle or actual measurements on the fractures themselves as they're sheared?
It would be not using characterization of a power law, self-affine fractal dimension like Thibaut Candela's work.
Okay.
It looks at roughnesses over 10 decades of length scales from micron to kilometer folds.
Okay, thank you.
That's the idea.
Other questions for Derek? So, the meeting can run for as long as we need. If there's any questions from the
baffled them with bullshit.
What was that?
I baffled them with bullshit. That's why I don't see any other questions.
I don't know about that. You stumbled me. So if there's any other questions, if there's questions from the R&D performers that you want to have to the Forge modeling team, most of the team are on the meeting. So if there's anything that pointed questions, or if we can't answer them, we can probably follow up later too. So any questions that as people get started, or things that input you'd like, or I guess the floor is open. So I'll just leave it at that. Okay, I realize on the West Coast, I'm standing between people in their lunch. So that's the last thing I want to do. So I guess we'll adjourn for today. If there's any topic that you would like to have discussed at an upcoming meeting, please send an email to the address on the chat, or email me directly if you need to, and we'll get it added. I mean, this is meant to be an informal discussion for advances, pitfalls, whatever we want to do. So we'll go.
Hey, Rob, I have a question. So earlier you mentioned and having sort of a standardized stress model, fluid chemistry, that sort of thing available for the reservoir. Obviously, for the modelers and the lab people, they want to be working with the same chemistries and stress states. And I know the stress model is a work in progress, but is there a plan to have some kind of place where people can go and see those values and not have to sort of discern them themselves from publications and that sort of thing?
No, so that's what the GDR is for. So the native, there is a published native state model. The last one that's on the GDR is from the end of phase 2C. The phase 3 update, the modeling work is complete. we are actually right now writing all of the revised text and getting the files ready to dump to the GDR. So the geochemistry models are just more like just batch type models, but the full 3D reservoir model for pressure, temperature, stress, the calibration are done to all the wells that we have at the site where we have data, and all the testing we have. That is complete. We're just working to essentially export it right now. The question, some of it is we actually work internally with a mesh format called Exodus 2, which is a pretty common finite element framework. We will also push it out into the Leapfrog software, and I can actually then extrapolate it onto a structured Cartesian mesh, and we can just share it out as ASCII point data. Those two things, keep posted. When we actually get those posted, which should be a matter of, I asked for an update by the end of next week from everyone. So we're talking in a matter of days to weeks to have all that available for the community. So
okay, and in there would be what we know now about fluid chemistry in the reservoir and state of stress.
Yeah, so the native state model does not do the chemistry across the entire reservoir domain. We did batch chemistry and batch equilibrium models. So the full 3 reservoir model doesn't have the chemistry. It's thermohydromechanic.
Yeah, well, I know that, but I was actually thinking of measurements. I mean, there people have been asking around about these sorts of things. What do we know about fluid chemistry in terms of, composition, for example, and what do we know about state of stress? We've all seen the Stanford geothermal paper, and we just want to know, and that's, of course, that's a topic of discussion among the awardees. And so I think having some simple explanation of where we are with the stress model and where we are with understanding of actual fluid chemistry in the reservoir fluids would be helpful to the lab people in particular, so they're looking at the right conditions.
For the stress model, Rob, if I may, so
Yeah.
we just submitted a paper to ARMA on some additional analysis of the stress state. So that just complements the work that was done with John McLennan had done with his team. So very similar in terms of the values and the regime. So that might be useful.
Does that amount involve reinterpreting the defits using different kinds of models? I know that Mark McLennan's been doing some of that too. So I'm just curious. I'd like to see a copy of that. That would be great.
Okay, yeah. So we took actually their DFIT data, but we're looking at a DFIT value also, because one of the results provides very high value, unexpectedly high for SHMIN. So we're looking at that one, but the rest are just drilling induced cracks and breakouts and stress polygon, blah blah blah. So,
okay, so kind of extending the work that was discussed at Stanford. Yeah, it'd be great to see that. Thanks. And I think the other people would be interested in this too. It's not just a me question.
Yeah. So there is the issue, I guess, that maybe as things get posted and pushed onto what was the preferred way to share data, the GDR, the geothermal data repository is not as how do I say this gently? It's not as conducive to getting out, clearly what people should be using. So I have an action here to get information on fluid chemistry, like measured chemistries. For the fluids, that has been done. We'll find the reports for that. Stress models, I'll ping John, and
also, that's what I was really referring to, Rob. Okay. I mean, I'm familiar with the GDR. It's just there's a lot of stuff in there.
Exactly, you're right.
And I just want to make sure that people are, know what the current state of the art is in terms of actual fluid chemistry in the reservoir and state of stress with uncertainties. Because if you're uncertain on the state of stress, it would be good to bound those values in the lab, for example.
Right. Okay. And that kind of reports have been written by others of the team, but I'll relay that information. And what I intend to do is, as people sign up for this meeting and attend, I'll have a user list, and I'm just going to use this as a mailing list to keep pushing stuff out, because it has all the R&D performers, at least they were invited, and anyone else who's interested, we'll just kind of keep pushing that information to that mailing list. The other, I guess, point to that is when we publish the revised native state model, I'll push that information out too and send links to where you can find them on the GDR. If you go to the Utah Forge website for the modeling and simulation, like what we did is actually that very thing, Steve. It's like for every boundary condition, every native or every initial boundary condition, all these things, we sent a picture, described it, and we have a link that goes to where to find the information. we'll be doing that exact same thing for the update of the model. That's just gonna take, as it gets through, it gets pushed out. But I'm not sure, we'll get the information to the web team, hopefully by the end of next week, and whatever time it takes them to get that updated, that'll be out there as well.
Okay, good. Thank you.
Okay.
Yeah, and Rob, on this stress deal, so we haven't uploaded it because John is reviewing
Okay,
the
perfect.
material. So once it's done, then you can upload it.
And that's, I like, we're going to see, that was kind of the intention. A lot of this is, at least we have what we're calling a reference set of everything. And then, people can go and experiment around that, make that reference better by giving feedback. But this is the current state that we are using as a Forge team for our stuff. And then, and we can go there. Because to be quite frank, the work that we do as a modeling team for the Forge itself, I don't want to say bare bones, but essentially, we're doing very programmatically based, just in time models to support activity at the site. We don't have the time or kind of the budget to take to do some of the fun work that I just saw presented here. So, it's more just, bread and butter kind of a modeling for production type work. So I'm really looking to the research teams to drive a lot of the innovation and bring more information into the whole paradigm.
Good, thanks.
All right. Other comments or questions? Well, I thank you. I'll try to send out a reminder and an agenda about a week before each recurring meeting. And you should see this since you're here today. That means I have your email address, and we'll go from there. So thanks for joining today.
Thank you. Goodbye.
All right. Bye now, everyone.